Okay, so what I have done is I have taken the definitions and I have written them out for you. And I have started with molarity and gone through solute. I'm going to scroll down and show you the rest, and then I'm going to open another page. You can pause these recordings so that you can see what the definitions are. I'm not going to take a lot of time to show you the definitions. They came out of the textbook, out of the notes, not anything new for you. So I'm going to go down to solute and let you see that section. And again, you can pause so you can read through it. And supersaturated gets finished on another page, so let me go there. There's the other page. Pause. You can look at them. I'm going to scroll on down. There's the remaining definitions. So that'll take care of all those terms that are talked about in number 1. I'm going to stop the recording. I'm going to pull up the rest of the review and continue to work. Okay, so I should be back now and able to talk about the review. We've already done number 1 when I showed you those definitions. Number 2 says that you need to know that like dissolve likes. Polar solutes dissolve in polar solvents. How do I know if something's polar or nonpolar? If it has a possible positive or negative end, it's polar. So something like an ionic compound would be polar. Water is a polar molecule, so water will dissolve ionic compounds. Nonpolar solutes dissolve in nonpolar solvents. Something is nonpolar if it does not have an obvious positive or negative end, so oil is nonpolar. So that is why oil will not dissolve in water. Oil and gasoline would both be nonpolar, so they could mix together well. Okay? So you've got to know if something is polar or nonpolar. It's that simple. You need to be able to, on number 3, discuss the solubility of gases as temperatures change and pressure changes. Think of a 2-liter soda and what happens when the soda is not chilled and you open it. You release the pressure by taking the cap off, and you get this tremendous fizzing of gas coming out of solution because it's warm. So it's not wanting to stay in solution anyway, but as long as the pressure is present, it'll stay in solution. As soon as you unscrew the cap, you get that fizzing because the gas has now an escape route. The pressure is less, and so the gas will come out of solution. Number 4 said, what was the reason that rock salt was added to the ice in the ice cream lab? Because what we were trying to do there is we were trying to depress the freezing point and get the ice to freeze at a lower point so our ice cream could be smoother and creamier in texture. So the fill in the blank says the addition of a solute to a solvent causes a depression, or decrease would work, in the freezing point and an elevation in the boiling point. And that's the reason we put coolant in our radiator of our vehicle, is we want to keep the water from freezing in the winter. Okay, so we want to keep the water from freezing in the winter because in some parts of the United States, believe it or not, the temperature gets below 40 in the winter and water freezes at 32, so we want to keep the water in our radiator from freezing. And in the summer, we want to make sure that the water doesn't boil out of our radiator. So we elevate the boiling point. Okay. All right, then number 5 says, think about the lab we did with potassium nitrate and water. What happened to the solubility of the potassium nitrate as we increased the temperature of the water? Well, when we made our graph, we saw a curve that looked something like that. So as the temperature went up that way, the solubility increased. What is the general trend between the rise in temperature of solvent and the solubility of the solid solute? As temp goes up, in general, the solubility should also rise. Okay. Okay, so the next one says, discuss the surface tension of water and what property of water allows for surface tension. So we know that the water has great surface tension, much more than most liquids. If you think about it, it is possible to have a bug walk across the surface of the water. also possible to take a paper clip and gently lay it across the water and it'll stay suspended and just hang on top of the water until someone smacks the water surface. And the reason that that is true is because of hydrogen bonding. If you look at a water droplet, it tends to be spherical in nature, and that's because there's nothing up here for the water molecules to bond to, so the forces pull inward and pull it into that spherical shape. All right. Number 7 says, why does ice have a lower density than water? Okay, so when we think about ice, when water freezes and becomes ice, the volume expands or enlarges. Didn't change the mass, just created more volume. And since density is equal to mass over volume, if the volume gets larger, but the mass remains constant, then the density decreases. Let's see if there's anything I need to add there. Nope. Okay. Be able to predict which compounds will dissolve in water, which compounds will not likely dissolve in water. So polar compounds. We talked about that up there on number 2. Tend to dissolve in water. So that would be anything that is ionic in nature. Like those ones that are the polyatomic ions on the back of the periodic table that you use in class all the time. Those will dissolve in water because they have a definite positive and negative end. Water molecule has a definite positive and negative end. They like each other, so there will be some dissolving going on. Okay, number 9 says, what is the molarity of a 245 grams of sulfuric acid dissolved in 1.8 liters of solution? Well, molarity, you have to remember, is moles over liters. However, you do not have moles right there, so we've got to get that into moles. So I'm going to say 245 grams of H2SO4. And then I'm going to use my periodic table to get my GFM. 1 mole of H2SO4 is 98.1 grams of H2SO4. That should cancel with that. So when I did 245 divided by 98.1, I got 2.5 moles. And then 2.5 moles divided by 1.8 liters, I got 1.39 molarity H2SO4. Sorry. Molarity of 5.3 grams, same thing. Can't use those grams, got to convert them into moles. And 1 mole of Na2CO3 has a gram formula mass of 106 grams. How did I know? I went to the periodic table. So those will cancel. And when I did that, I got 0.05 moles. But they wanted molarity, so I said 0.05 moles over, now be careful here because this is in milliliters, put it in liters, 0.400 liters, because there's 1,000 milliliters in a liter, so I took 400 and divided it by 1,000. That's how I got that number. When I did 0.05 divided by 0.4, I got my molarity to be 0.125 molarity Na2CO3. And that's a 0 right there. Doesn't look like one. Okay, how many moles of Na2CO3 are there in 10 liters of a 2 molar solution? So 2 molar is equal to moles over 10 liters. So that tells me that I have 20 moles. And I want 2 significant digits, so I should just say 20 moles of Na2CO3. So there's that correct answer. There's that correct answer. And there's that correct answer. Okay, how many moles of Na2CO3 are there in 10 milliliters of a 2 molar solution? Okay, so this time I have milliliters. Convert those milliliters to liters. 1 liter is 1,000 milliliters. So I'm going to have 0.010 liters I need the moles again, so I'm going to say 2.0 molarity is equal to moles over 0.010 liters. So when I do that math, I'm going to get 0.02 moles of Na2CO3. And I'm going to pause and move on down. Okay, the next question says, what weight in grams of Na2CO3 would be contained in problem 11? Well, if you go back to problem 11, we had 20 moles. 1 mole is 106 grams. So 106.0 I should have said. So if I multiply 20 times 106.0, I'm going to get 2,120 grams of Na2CO3. And I want 3 significant digits, so that works out grand. Good answer there. Okay, what weight in grams of H2SO4 would be needed to make a 750 milliliters of 2.00 molarity? So I'm going to say, well, 2.00 molarity, capital M, sorry, is equal to moles over, now milliliters has to be in liters, so that's 0.750 liters. So I multiplied 20 times 0.7, or 2 times 0.75, I'm sorry, so that gave me 1.5 moles. But they don't want moles, they want grams, so I said that 1 mole was 98.1 grams of H2SO4. And so when I did that math, I got 147 grams of H2SO4. All right. We're going to just stop right there, and then we'll come back and do another one.